Hi, everyone, and welcome to Web Application Security Trends, the never-ending tale. My name is Christian Wenz, and I'm excited to be here at DevDays Europe, and wish we could all see each other in person. But, well, for now, a virtual meeting must suffice, but next year will be better, I promise. And with that, I switch over to my screen, where I have a couple of slides with a couple of, web security trends, as the name already suggests. And so the actual plan for the session is that I will show you some maybe new or updated or just interesting aspects of web application security. Some maybe rather new attacks or rather new countermeasures or both, or old attacks with new twists. And even though you might know one or the other attack, I'm certain that there will be some new, valuable, and maybe also amusing, fun information for you. So the next 40 minutes or so will be well worth your time. I will watch out for the chat window and especially Q&A window. So if there are any questions, I'll either answer them right away or in the last few minutes. And with that, let's start our whirlwind tour through the ever-changing web application security scene by one of the oldest attacks around, cross-site scripting. This might come as a surprise because, I mean, cross-site scripting exists since 1999, 2000. Back then, the name of the attack was coined cross-site scripting, which is a rather stupid name, something like JavaScript injection or HTML and JavaScript injection would have been much better because it just describes really well what the attack is all about, at least in most cases. But well, there we are talking about cross-site scripting, and I started doing web app security in about 2001. And you see here in the chart that I went to cvdetails.com, where they plug into the database of the CVEs, the common vulnerabilities and exposures. That's a list of publicly disclosed security issues and vulnerabilities. And then I filtered for cross-site scripting. And this is the chart for cross-site scripting. So the number of cross-site scripting vulnerabilities found in that year. So I started in 2001 and thought, oh, well, that's interesting. So let's do this for a few years. But eventually, the situation will get better. Turns out the situation got much worse. So in 2006, there was a new record number of vulnerabilities. And then the numbers continued to decline. And so in 2011, 10 years after I started with this topic, I thought, okay, this might actually be it. Tools have become better, developers have become better, frameworks have become better. This is the end of cross-site scripting. And since 2011, each year I say, okay, this is the end of cross-site scripting, and just look at the numbers. So we had a new record high in 2019, very, very high values in 2020. And well, the low values in 2021, it's just at the right end of the chart. They can just be explained by, well, we aren't even halfway through the year. So it looks like new almost record numbers for this year as well. So cross-site scripting, for some reason, does not seem to die. And I'd like to show you a few maybe surprising features of cross-site scripting, because I do a lot of audits. I mean, I'm often called prior to an audit or after an audit, but I also do an audit. And there's some, I mean, depending on the stack, some of the attacks are more common than others, but regular cross-site scripting is rather hard to find, which basically is a good thing. Often thanks to the framework being used and countermeasures built in there. But unusual cross-site scripting is something I find more and more often. And so maybe a few surprising aspects. And countermeasures. So the Open Web Application Security Project, they once defined 3 types of cross-site scripting. And the most common types and those which you usually see in demos are type 1 and type 2. Type 1 is persistent cross-site scripting, where the web application stores the malicious code. Non-persistent or reflective cross-site scripting, type 2, is where the application echoes back the data that you send to it. And so usually you put the malicious, let's say, JavaScript code in the URL, and the web application just outputs parts of the URL verbatim, and then you send that malicious link to someone else, and then they got cross-site scripting. However, there's also DOM-based cross-site scripting, and that's where there is no server involved. So everything happens in the client. For single-page applications, this might be quite a danger, because in single-page applications, once the application is loaded, communication with the server only happens via API calls, at least usually. However, often there is data being appended to the URL, and then the JavaScript code reads out that data and does something with the data. And this sometimes might get exploited. And I don't want to show you DOM-based cross-site scripting today, but I thought I would show you something kind of related, but it's regular cross-site scripting, so to speak, or actually non-persistent cross-site scripting, but it uses a twist, because what I guess you all have learned is that to beat cross-site scripting, you have to escape output. So in an HTML context, you have to escape the 5 special characters of HTML. Angular brackets, opening and closing, single quotes, double quotes, and the ampersand character, because it starts entities. And that's correct. But the part of the sentence that's often overlooked or ignored is the in an HTML context. So actually, let's have a look. I have here an application, and this application is done in ASP.NET MVC, and in an old version, I need this because I'd like to make some things rather obvious, but it really doesn't depend on the stack. And what I'm doing here is I have an HTML page, and I'm loading jQuery, and then I have an output placeholder here, the span element. And once the DOM is ready, I basically say, okay, please access this output element, and then write something into it. And what I write into it is part of the view bag. Basically, I have some code in the backend which reads out parts of the URL of the query string and then puts it in that viewbag.name variable. And when I output this, I use the colon syntax. So what the colon syntax does is it escapes HTML special characters, right? So how about we try this out right away. So I go to this page. Okay, and then I append, and I hope you can read it via the stream, but I tell you what I'm typing. So name equals, and let's say Christian, my name. And you see Christian is the output, and why in the markup. This here was written into the JavaScript code by the logic I just showed you. So how about we try cross-site scripting? So we go back in the URL and I do a script alert1 script. And then we see the text here. So there is no JavaScript code, which I injected just the text. Why? Because I am HTML encoding the angle brackets here using the colon syntax. So no cross-site scripting, right? Super secure. And the problem is, remember, we escape HTML special characters because they have a special meaning in HTML, as the name suggests. However, we are not in HTML here. We are in JavaScript. To be specific, we are in a JavaScript string. There are certain special characters in a JavaScript string, for instance, single quotes, but single quotes happen to be an HTML special character as well. It's a delimiter for attribute values, so we are safe. But there's also the backslash character. So if I, let's say, append a backslash character in here, and we just look at the source code, you see the backslash character is output here without any escaping. It happens to escape the single quote here, so we have a syntax error. Syntax error is not that much of a problem yet, but with the backslash, I can also use escape sequences within a JavaScript string. For instance, \x allows me to use character codes. And remember, the angle brackets here, they were replaced by entities LT and GT. But I could use the char code. Now, what is the char code of angle brackets? I don't know. So I go to asciitable.com. And then I see here, okay, opening angle bracket is 3C and 3E is closing angle bracket. Okay, I can do that. So I go back here and I replace the opening angle bracket with \x3C, \x3E for the closing one. Same thing here at the end, \x3C, \x3E. Bam, cross-site scripting. Although I did HTML escape. And if you look at the source code, you see here, that's an opening angle bracket. But it is not a verbatim angle bracket here, so the escaping doesn't work, and I don't escape the backslash, because I only escape for an HTML context. Now I'm using .NET here, and in .NET there is a specific escaping method for a JavaScript context. JavaScript string escape, very long name, in the HTTP utility class, but you have to do it, right? So all of this HTML escaping is safe in an HTML context, but only there. And if you're in the situation that you have inline JavaScript code, which is usually bad anyway, and you have to use user-supplied data in that JavaScript code, find a way to do it differently, or just do super strict validation of the input, and of course, properly escape the output. So this is kind of cross-site scripting that is maybe a bit unusual and a bit surprising, and that just shows that there are so many flavors of cross-site scripting that doesn't seem to go away. And by the way, why is there still cross-site scripting? I mean, what's the problem with alert 1? Alert 1 is not really a threat, it's just embarrassing for me. But of course, cross-site scripting is super dangerous. But if you see a lot of alert 1s, and today you will, I'm sorry, probably you think, oh no, that's not much of a problem, but it is. And the reason for that is the same origin policy. The same origin policy is basically the one security mechanism for JavaScript code. In layman's terms, it says JavaScript code can only access things, quote unquote, that have the same origin. And the origin is essentially protocol, domain, and port. I don't like the term origin, but we'll talk about it in a bit. So assume this page here, example.com port 80, some random page. And on this page, there are 3 blocks of JavaScript that are supposed to be executed. Top left, we have inline JavaScript code. Top right, we have an external file on our server. And bottom right, we have a JavaScript library. So here I was taking jQuery from a CDN, right? So I use it from a CDN so that I don't have to pay for hosting. Well, if you follow the news today, there's major internet outage, at least for some websites, because one of the big CDNs has issues today. So it's not always the best idea to load this from the CDN. Again, your mileage may vary. But back to these 3 pieces of JavaScript code. So what is the origin, protocol, domain, and port of those 3 JavaScript blocks? For the inline code, I think it's obvious. It must be the origin of the HTML page. So http example.com and port 80. For the script file that resides on our own server, it will be the same because it's http example.com and port 80. But what about jQuery? Now, the intuitive answer to the question, what is the origin of that file, would be, yeah, it's https code.jquery.com and then port 443. But if that was the case, then the jQuery code would not be able to access any DOM elements on example.com. If you've worked with jQuery or any other JavaScript library, you probably have found out that even though you're loading the JavaScript library from a CDN, it still works. And that's why the origin here in this context of the same origin policy of jQuery is http example.com port 80. The origin in SOP terms is the origin of the HTML page that includes or loads the JavaScript code. And that's why I don't like the term origin, because intuitively you give the incorrect answer. I prefer the term security context. So all of these 3 JavaScript blocks run in the same security context, and that's the very problem of cross-site scripting. Because if someone is injecting code, it's either inline code, top left, or it's a JavaScript file on some other server, bottom right, and they both run with the same privileges as our own code. That's why JavaScript injection actually would be a better term. But so that's the reason, or the basic reason or background for that. And turns out there might be a chance against cross-site scripting, despite the really crazy high numbers of cross-site scripting that you saw before, and that is content security policy. Content security policy is a W3C standard, which is supported in all modern browsers, plus even in IE 10 and 11, but yeah, only one feature. And I'm not exaggerating here, one feature, and the users want two. So let's just skip that browser. All modern browsers do support content security policy. And content security policy is a so-called defense in depth mechanism, which essentially means it's just an additional layer of security. So content security policy is not an excuse for not doing anything against cross-site scripting in your application. It's an additional protection. So if IE 11 must be supported by your application, but is not supporting content security policy, that's not a problem. There's just no additional protection for your app. But all the other modern browsers just then can enjoy an additional and actually pretty good protection. I'll quickly show you how content security policy works, and also when or why it doesn't work. And for that, I have prepared an enterprisey application, which you are seeing here. So let's check out the source code for that, will we? So I have here a page, and on that page, first of all, I have the conference logo, and I don't like to pay for hosting, so I'm lifting it from the conference website. And I give it a nice background color, light gray, because I'm an amazing designer. No, I'm not. Then I have here a div element where I display the time. Then I'm using the underscore JavaScript library as my templating engine, and then have some extra codes. And then I call or I execute some code every 1000 milliseconds. And what do? I open an endpoint on my server once per second. And that endpoint will give me the current time. And then I use the underscore JS library in order to display that time, right? So that's all that's happening here. So trivial application, but I tried to make this a little bit confusing. And making it confusing makes it a bit harder to implement content security policy here. Because what does content security policy do? You see here a very simple example. Content security policy is an HTTP header, the one with the dashes. And the server sends this header, obviously. And the value of that header is a list of so-called directives. Directives are the things with the dash in it, so default -src. And most directives can have values, and the values are following the directives separated by spaces. The default SRC directive basically says whenever you load a resource, JavaScript code, style sheets, fonts, videos, etc., only use the following list of origins or sources. And things in single quotes are constants in content security policy. So basically this says whatever you're loading, only load it from the current origin, from the current server. That sounds like a logical thing to do. So let's implement this. So I use default -src single quote self, and then write out a content security HTTP header with exactly that content security policy, and let's see what's happening. And you see, okay, the time is gone, the font is smaller, and the logo is gone. And I think we can solve the riddle of the vanishing logo right away, because remember, I was stealing the logo from that server. So I should add this server to the list of allowed sources for content. I could use default SRC, but I could also use something specific, because for specific types of resources, there are specific directives. For images, it's image-src. And I could say, okay, load images from our own server and from DevDays LT. So I'm allowing the conference server for images, and therefore, yay, the logo is back. The gray color is not back, the time is not back, the font size is not back. So there's still some things to do, but let's stop here for a second and consider what we've just done. We've told all modern browsers that if they are loading resources, they shall only load it from a specific list of servers, so from our own server. Let's imagine we have a cross-site scripting vulnerability now in our code. How does it usually look? Well, it would be script src equals http attackerserver.org/badscript.js. But that code is not loaded or executed now any longer because attackerserver.org is not in our allow list, right? So that attack vector more or less completely vanishes, even though we have a cross-site scripting vulnerability in our code. And even better, at least from a cross-site scripting standpoint, when we have a content security policy that handles JavaScript code, which means we have a content security policy with default SRC, because that encompasses everything, or script-src, that's the specific directive for JavaScript code. Then, among other things, inline code ceases to work. And let's think about that with regards to cross-site scripting. So inline code doesn't work either. If someone injects script alert 1, that code does not run. So how can an attacker now possibly execute a cross-site scripting attack against our web application? Only if the attacker manages to inject script src equals badscript.js. And badscript.js resides on our own web server, but if an attacker can do that, cross-site scripting might be the least of our problems. An attacker writing files to our web server might be the graver challenge or catastrophe, right? So essentially, content security policy allows us to have a super effective safeguard against cross-site scripting, especially for recent applications and for new applications that are started with content security policy in mind. For legacy application, it's harder because if you look at the application I created here intentionally, we have inline styles. So inline styles, they basically vanish as well when we have a content security policy for style sheets. Inline code. Then we have eval, right? We have a string of code here, and that's automatically evaluated at runtime. This is also automatically deactivated with a content security policy. So a lot of refactoring has to go on in order to make everything happen here. And depending on how old your application is, it's a bit more work. I recently completed helping a company making one of their super important but super legacy applications ready for content security policy, and it took us a few weeks, but it really was so worth the effort. But still, it's not trivial. But this might be the best shot we ever had at beating cross-site scripting as an attack. But content security policy, and I like to finish with that, is not automatically, let's say, safe by itself. And I'd like to give you another short example here. So I have a page here, and that page is outputting some data, and it's outputting it with the equal sign, which means that there is no escaping, right? So I could send script alert 1, and it would not be escaped. So actually, let's try this out. So we have revoke, and then URL equals script alert 1. Then nothing is happening. There is the script block now, but the content security policy just saved us. The content security policy, as you see in the console here, refused to execute inline script, right? So we were protected. Does that mean there is no cross-site scripting on this page, which I can actively exploit with a modern browser? Well, turns out, if we look at the code here, the policy looks like this: script src self, right? But I also allow a different domain here, accounts.google.com, right? Because I'm using a script from there, and it's just an arbitrary example. Now, it turns out that on that server, there is a JSON P endpoint. JSON P, if you recall, JSON with padding, that's basically an endpoint which accepts a string of JavaScript code and returns a script file with exactly that code in it. So what I can do now is this, and I hope you can see it. As a parameter, I'm now sending a script tag to an endpoint on accounts.google.com, and I just use alert1 as the parameter. And now I have cross-site scripting again, because with the content security policy, I allow code from that server to be executed, right? So content security policy is no silver bullet, and you should not put too many of those servers or origins on the allow list, right? And there are other types of cross-site scripting that might be worth interesting. So, for instance, templating injection when you're using a framework like AngularJS. So, AngularJS, for instance, doesn't have a protection against cross-site scripting its templates. Angular does, right? So, newer versions do. And there are some other more recent developments or some things that just don't seem to die. I just would like to briefly point out one of this, mutation cross-site scripting, MXSS. Someone called Gareth Hayes came up with this specific attack. So look at this. It's a div element, right? And I mean, the syntax is just incorrect. There's a single quote that's never closed, obviously, and yeah, really looks really weird and really strange. But remember that browsers always try to fix everything for us, right? So if we write incorrect HTML or markup or whatever, browsers try to compensate, and they compensate here as well. So this ampersand hash 39 is the closing single quote, and then the GT is a closing angle bracket, and then we have an opening bracket, and then we have an iframe, and the iframe has the attribute onload equals alert1. And even though there is a slash in between, which is against the norm, the browser still interpret this, or at least some do, as iframe onload equals alert1. So we have cross-site scripting again, but it's not cross-site scripting from the beginning. It's cross-site scripting by the mutation that happens with that markup in the browser. And browsers are really hard to predict. Let me put it that way. So a lot of flavors, but I think with content security policy, we do have the best shot we've ever had. Another attack that's a bit more recent than cross-site scripting, but still old, is cross-site request forgery. And I think the technique itself is rather obvious, right? So I, as the victim, go to some attacker's website, and the attacker's website then basically redirects me to a third-party website, and I'm already logged into that third-party website. Due to the redirect, my browser sends an HTTP request to the third-party website. The credentials, so for instance, the session cookie or auth cookie, that is automatically sent by the browser. That's how cookies work, right? So the third-party website sees my request and says, well, that's a legitimate request. Let's do this. Let's delete the user, or let's put something in the shopping cart. And that's an old attack, right? But I still find it a lot, even though it dropped out of the OWASP top 10 list in 2017. And the usual countermeasures include adding a random token to those HTTP requests, and also persisting that token on the server, so that the server can decide whether it's really the correct random token that was sent alongside the request. But the main prerequisite of that attack is that the browser automatically sends the third-party website's cookies I have in step 3 of that process here. Turns out, so if you come from an attacker website and then are directly redirected, get redirect, or a post form that is submitted via JavaScript, and then get redirected to a third-party website, in that specific case, does it really make sense to send cookies along with that automatically? Sometimes yes, sometimes no. And well, there have been some recent developments, and maybe you had some issues or fun with that as well. And I'm of course talking about same-site cookies, also called first-party cookies. The idea is when I have a cross-site request, so I come from site A, and then from there do an HTTP request to site B, are cookies automatically being sent along? The default for when were cookies invented? 1995. So for over 25 years, the default was yes, of course. But now things changed. With the same site flag in cookies, you can set 3 different protection levels. One is the lax level. So for GET requests, cookies are sent along, which is okay. According to the REST principle, GET requests don't change the state of the application. So that works, but for POST, the cookies are not sent along. Then there is strict. So I have no cookies are sent alongside that request, and then there's none, which means there's no protection at all. It's the old default behavior. And Chrome started to introduce lax as default if you don't set it to a different value, starting with Chrome 80, and then the pandemic hit, so they retracted, and then they delayed the rollout. And now since Chrome 85, the lax is the default, and the current stable version is Chrome 91. And with 91, the options to change the behavior vanished, right? So starting like last week, this is what we need to work with. So if you require that cookies are sent along because you have some strange single sign-on setup, or some not so strange single sign-on setup, then you need to set the cookie value, same site value, to none. Except for certain Safari browsers, which interpret same site equals none as same site equals strict. So after 20 years of browser agnostic development, I'm again back to browser discrimination on the server and trying to find out which browser is talking to me. Oh well. From a cross-site request forgery standpoint, that's of course pretty awesome, right? Because we have an additional layer of defense against this attack because the cookies are not sent alongside the request any longer. So here on localhost, I have a couple of cookies, a strict and a lax one, and someone without protection. And you see here in the Chrome DevTools, I hope you can see, let me actually beef up the font size a little bit. So strict, lax, and, well, default behavior. And then when I go here on my other server, I can, for instance, do a post request to a page that basically reads out the cookies. So you saw I jumped from .NET to PHP, and I see no cookies here, right? Because I was doing a post request, and then those cookies with the same site values being set, and also default behavior, they were just not shown to me, right? When I do a GET request, then I can access at least 2 of the cookies, the regular one and the lax one, but not the strict one. So quite effective tool. It's a bit of a nuisance that it's now the default behavior for Chrome because it required us to change our working applications to still comply with the browser. And there are also some interesting exceptions, like if you create a cookie and then do a cross-site post request in the next 2 minutes, then this cookie will still be sent along for some single sign-on scenarios, but that's also a workaround that will eventually vanish. The Firefox team has also announced that they will default to lax same-site settings in quite a bit. Now, another thing that people talk about a lot, but depending on the stack might not be a problem at all, is something called XXE XML External Entities. So the idea is this: I have an application that accepts XML and then parses the XML and then does something with it. And of course, some of you might say, XML, what's that again? I'm only using JSON, my friend. I've no idea what you're talking about, and it's completely valid, right? But if you do, and especially if you have older stacks, then something might happen if, for the attacker, the stars are aligned correctly, and I'll show you a quick example. Actually, let's pick that file today. And here, I have a page, and that page, well, basically outputs some data and HTML escapes it. So that's not too exciting. A bit more exciting is maybe the code. To make things easier, I just read in an XML file. Of course, when the attack actually takes place, the XML is sent in the HTTP request. But to make things easier, I just created the XML file, and then the XML file is basically loaded, and then it's returned to the page. Let's have a look at the file, and the XML file looks like this. It's using a tag as an element. Well, I define it here. That's of course not a standard XML element. And within that element, I have an entity, ampersand XXE semicolon. That's not an entity I've ever heard of before. However, I happen to define it here in that XML file as a system entity, and the system entity points to a specific file on my server. This could also be a URL. Now, if the logic here is parsing that XML file, it sees the entity and then resolves the entity, so it basically loads or includes the file or does an HTTP request. Interesting. Let's try this out. So XXE, and you see here that now the XML basically contains the contents of my password file. That's my password file. Extra credits if you recognize where I took this from. And that's XML External Entities, right? And this is super frightening. It's number 4 on the OWASP top 10, but I had to cheat a little bit in order to be able to show you this, because a modern stack is protected. So for instance, PHP, the latest version, doesn't allow developers to activate this resolve entity feature, because in the library they're using, this has been disabled since 9 years. .NET is secure since version 4.5.2. And remember, after 4.5 came 4.6, 4.7, 4.8, core 1, 2, 3, 5, and in fall 6, right? So this, if you have a modern stack or the right stack, quote unquote, then this is not really a problem for you. And the attack that can be carried through if XXE is possible is sometimes also called server-side request forgery. So basically, the attacker sends a request to our server, for instance, with the XML, we parse it, and this then leads us to send an HTTP request to, say, an internal system, because the entity in the XML file resolves to a URL, an internal URL. Obviously, as an attacker, you have to know exactly either how local files are named on the server or what the URLs for internal systems are. So maybe you're an ex-employee, I don't know. And of course, you have to have an application that is using that XML then and is actually parsing it, and maybe, like in my example, then returning the file. So really, a lot of things have to work exactly as intended by the attacker. Otherwise, this attack would be futile, right? But I just wanted to mention it because I do see this a lot. I would like to let's have a look at an attack which I call phishing via external links. And once again, I'll just show you how the attack works. And that's super interesting because it's abusing a feature that was introduced in about 1995, 96 in, I guess, Netscape 3. But I think it took then attackers 23 years to find an exploit or a good use for that feature. Simple example. Let's just imagine this is the Instagram profile of someone, right? The conference's Instagram profile. I don't know if the conference is on Instagram. Let's just assume it. And on your Instagram profile, you can provide a link, right? A link to, say, your homepage, right? So what happens if I click on that link? Well, the homepage of the conference or the target site opens up in a new browser tab, right? And so it does, okay? Now, what is your expectation if you close this browser tab? Of course, the expectation is that you then, the browser tab is closed, you see this tab here to the left, and the tab is your Instagram page, just like before. This is the page the attacker controls. The tab we just saw before, which is now currently hidden or not visible, is Instagram, which we cannot control. So I close this tab and see what's happening. Nothing. Oh, that's a bummer, right? That's exactly the behavior we expected. But I was poking fun at one specific browser today. And so how about we pull up this browser, right? Again, opening my homepage. Okay, I'm closing the tab. I have to log in again at Instagram. What was happening here? I mean, what you see, I can't even go back, right? The back forward buttons are deactivated. It's like if I started on that page. And what happened here is this. Let's have a look at this page, which is open, which I can control. In the markup, let's have a look at the markup in the other browser. In the markup, what I'm doing is I access the opening tab, and due to the same origin policy, I mean, now here's all on the same system, but in reality, this would be an external web server. In reality, the same origin policy would prevent me from accessing, say, the DOM of the opening page. And of course, that's a good thing, right? But here, I can still access the window element and the location. And then just replace the location with here another page. So I'm redirecting the original tab. And I mean, if it didn't say, welcome to my, what was it? Welcome to my phishing profile, but instead, oh, you have been logged out, timeout, please log in again. Probably no one would take a close look at the URL if the URL was still the same, but would just say, I mean, I just was here on Instagram. Yeah, of course, that's the genuine Instagram website. I don't have to check the domain or the URL. I just type in my credentials. And then your credentials are essentially gone. And this attack actually was possible against Instagram. So they were ones of those where this was exploited. And to beat this attack, you had to add rel equals no opener to all external links. So just linking to an external page you don't control is a security threat, which is just insane. And that's why in Chrome 88, now we're at 91, and in Firefox 79 and higher, rel equals no opener is now the default value. So you don't have to specifically add this this attribute any longer if you don't want to, right? So even the simplest things, such as simple links, can pose a security threat. But thankfully, there are not only new threats, but new countermeasures like rel equals no opener, content security policy against cross-site scripting, SameSite-Cookies against content security, cross-site request forgery, and there are more HTTP headers which are being added to browsers to make them even more secure. For instance, feature policy, or now it's a successor permissions policy, which basically restricts which JavaScript APIs a website may call, referrer policy, so in which HTTP request should include which parts of your referrers. Recent Firefox versions also limited the amount of information that's leaked when you do a cross-site request when it comes to the referrer. And then there are several cross-origin policies, cross-origin embedder policy, opener policy, resource policy, which is always relevant for when there's a cross-site or cross-domain request, which resources, for instance, should be sent or should be delivered. So a lot of stuff is going on in browsers. And if you look at the numbers at the beginning, it's important that they do because web application security is still a topic and is still a trend. The whole topic is a trend, and I hope I was able to show you some aspects that might be surprising or at least very valuable for your daily work. With that, let me check the Q&A section once again. I don't see anything in there. If you have any questions, still to ask them in the chat, or send me an email, or tomorrow morning, please, I think at 8:05, if I'm not mistaken, there is a security roundtable. So there's a panel discussion with a couple of people, including myself. So if you have any security questions or are just interested in the field and the developments and what people are doing, I invite you to come, and would love to see as many of you as possible in that session. And with that, all that remains to be said is thank you very much for your kind attention and for your attendance. Hope you enjoy DevDays Europe and the remaining talks and the remaining content of the conference. And I would love to see you all again, hopefully in person, next year at next year's conference. And with that, have a great day, and please stay healthy and stay safe. Thank you very much.